Study guide for test 3. Find the remainder of 482 mod 16. We find the quotient by dividing the number 482 by 16 and taking the floor. So the quotient is 30 and the remainder is this difference. From the number you subtract 16 times the quotient. The result is 2, so the remainder is 2. Problem 2. Use mathematical induction to prove that the sum of the cubes of the first n positive integers is equal to n squared times n plus 1 squared divided by 4. The basic step, we check that the statement is true when n is equal to 1. It becomes 1 cubed equals 1 squared times 2 squared divided by 4, which is obviously true. The inductive step. Let k be a positive integer. We assume that the statement is true for n equals k, that is, this equality holds. And we have to prove that the statement is true for the next value of n, k plus 1. This is the statement we want to prove. It is obtained from the original statement with replacing n with k plus 1. Because of the assumption, the sum of the cube of the first k positive integers is equal to this expression, and we can replace it. So our equality becomes this. If we prove this, the equality that we want to prove will follow. They are equivalent under the assumption. Then we divide both sides by k plus 1 squared to simplify the equality. We obtain equivalent equality. Then get rid of denominators, multiplying by 4. The result is an equivalent equality. Multiply out here, you get this. And obviously, if you expand k plus 1 squared, you'll obtain the left-hand side. Since this equality is true, the inductive step is completed and the statement is true for all positive integers n. A recursive algorithm for computing the GCD of A and B is provided. It is this procedure. The basic case is when A is 0, then the output is B. And in the else statement of this if operator, the algorithm calls itself with values, the remainder of B mod A and A. Trace this algorithm when it finds the GCD of 12 and 30. The algorithm uses the else clause when it is invoked because A is not 0. It replaces A with the first number with 30 mod 12 and the second number becomes 12. So the algorithm calls itself for these two values, 6 and 12. Again, the else clause of the if statement is used because 6 is not 0. The algorithm calls itself with these two numbers, 12 mod 6 and 6. 12 mod 6 is 0, so this is the call. When the algorithm is called for these values, the output is 6. because the first number is 0. So the output is 6 for the whole problem. Find the recurrence relation for a sub n, the number of bit strings of length n which contain 3 consecutive zeros. What are the initial conditions? Find a sub 6. We count the good strings that satisfy the requirements. For n at least 4, we'll obtain a recurrence relation. The last digit of a good n-bit string is either 1 or 0. If it is 1, then we have a sub n minus 1 good n-bit strings, because if we write at the end of each good string of length n minus 1 at the end, it becomes a good n-bit string, and vice versa. Any good n-bit string that ends with 1 can be obtained this way. Then the n-bit string ending with 0 split into 3 disjoint subsets. If the next to the last digit is 1, we get the first subset, and subset 2 and 3, the next to the last digit in those is 0, but they differ for the third last digit. In subset 2, the third last digit is 1, in subset 3, the third last digit is 0. Similarly, we obtain the number of good strings in the first two cases to be a sub n minus 2 and a sub n minus 3. In the last case, because we already have 3 consecutive zeros at the end, it doesn't matter how I fill out the first n minus 3 bits, the result always will be a good n-bit string. And n minus 3 bits can be filled out in 2 to the n minus 3 different ways. So the recurrence relation becomes this: a sub n is equal to a sub n minus 1 plus a sub n minus 2 plus a sub n minus 3 plus 2 to the power n minus 3. A1 and A2 are zeros because we don't have 3 bits at all. And A3 is 1 because only 0, 0, 0 is a good string of length 3. So these are the initial conditions. And for C, we first find A4, just replacing the recurrence relation n with 4, we have this. And we know everything to the right hand side, so we get 3. For A5, we replace in this recurrence relation n with 5, we get this equality. And again, to the right hand side, everything is known, so we evaluate, we get 8. And finally, replace n with 6 here, you get this. And again, everything to the right of the equality is known, already computed here. A5 is 8, A4 is 3, and we get 20. So the answer for C is 20. Problem 5. Solve the recurrence relation with the initial conditions A0 equals 1, 1 equals 0. The characteristic equation is obtained from the recurrence relation because the difference between n and n minus 2 is 2. We get a quadratic characteristic equation. You replace here an with r squared, n minus 1 with r, n minus 2 with 1. Then move all terms to the left-hand side, you get this equation. You solve this quadratic equation. It has two different zeros, 2 and 3 in this case. The theorem says any sequence that satisfies this recurrence relation has nth term in this form where C1 and C2 are some constants. You fix those constants, you get a sequence that satisfies this recurrence relation. And we have to select appropriate coefficients C1 and C2 so that the initial conditions given in the problem are satisfied. A naught, replace n with 0, you get a naught. But this becomes C1 plus C2 equals 1, the first equation. Then replace in the formula that we have n with 1, you get a1, which is 0 in the problem. So 2c1 plus 3c2 is equal to 0. And we have to solve this linear system. If you multiply the first equation by -3 and add the result to the second equation, you'll get negative c1 equals -3, so c1 is 3, and in that case c2 must be -2. So replace the coefficients in the formula, you get this sequence. It satisfies the recurrence relation and the initial conditions. And you can check that this is the case by evaluating this expression when n is 2. You'll get -6 here, and then go back and you find the second term of this sequence. A2 will be 5 times 0 minus 6 times 1, -6. So they coincide. Problem 6. Solve the recurrence relation with these initial conditions. This recurrence relation with the initial conditions defines a unique sequence. You can compute the next term, A2, easily. A2 will be -4 A1, which is 2, minus 4 A0, which is 6. And the result is -32. So it is similar to the previous problem, and you find the characteristic equation similarly. Replace an with r squared, an minus 1 with r, and an minus 2 with 1. Move each term to the left-hand side, and you get this equation. Quadratic equation, easy to solve. It has a repeated 0. And here is the difference. In the previous problem we had two different zeros. Now we have a repeated 0. So another theorem applies when the characteristic equation has repeated zeros. It says